Should be working.
Should be working. I think. Okay, so maybe we can talk about that more offline, and let's get back to the actual lecture portion of the lecture. Okay, right. So, right, here's a good example of, just as before, when we had a contradictory assumption, we had 1 equals 2, right? If we have the false as an assumption, we can immediately prove anything we want. And this is what we see here with this ex falso quod libet, which means in Latin literally from false follows everything. I probably mispronounced it, but given that Latin is a dead language, I don't think anyone is really going to mind. So here, if we have, so we say for all possible propositions, that is for all statements, assuming false, we can prove that statement, right? So we can introduce, we call intros, and now we have this contradictory assumption false. So if we use, if we say destruct on contra, it immediately solves the goal. And this is true for any goal. If you have false, you can call destruct on it, and it will immediately solve the goal you're working on. We could have, yes?
Every year in Vatican City, there is a Latin as a live language conference that has more people than in this room.
Okay, the statement was that Latin is alive and well in Vatican City. And it is a valid statement. So I retract my early one.
More users right now.
Yes, anyway. I will also note that just as we could have also used the inversion tactic to discharge this contradictory assumption. It works, sorry, it would have worked just as well as calling destruct on false. Yeah?
Inversion is for injectivity and disjointness, and because there is no constructors, this works fine? Why would
The question was, why does inversion work on this goal? And maybe I should have introduced this, this formulation, but yes, because false has no constructors, inversion immediately solves the goal. That's the reason why. You can imagine that inversion is one of the many things in inversion's large hammer is it calls destruct. It uses destruct. Is the right, I think, the right intuition there. Okay. Okay, right. So here's an example of a theorem we might want to prove about some fact that is not true, right? We might want to prove that 0 equals 1 is false. So recall that this not symbol here just expands into 0 equals 1 implies false, right? So how can we prove this goal? Well, we'll introduce as an assumption that 0 equals 1, and our remaining goal is going to be not. And once we have 0 equals 1, we can call inversion on it because it's a contradiction, and it'll immediately discharge.
We have a type class for types that we know how to build generators for. And the one operation in that type class, following Haskell's terminology, is called arbitrary. And now we can make gen instances for all of the things that we've built generators for. And then it's also convenient to have a type class that packages together both generation and shrinking, because we typically need both of them together. So the arbitrary type class does that. Okay, and now to test, for example, this conjecture that every color is red, we have essentially everything we need. We just need a decidability instance for colors. And now the type class machinery just gives us the arbitrary instance automatically. Okay, so putting it all together, we can easily find out that not every color is red. Okay, how are we doing? Good. So one other thing, I'm just going to run through a couple more kind of useful refinements. If we want to build an arbitrary instance for trees, what we need to use is the sized tree generator. And since we know that the G monad already carries along internally a size, what we want is a way of plugging that size into the size argument of the gentree sized combinator. And that's easy to do, so we can write a little function sized that takes a sized generator and returns a generator. Right, and it does it by just looking inside the definition of what G is to get at that size parameter that G carries along. And this leads us to ask for one more type class called gen-sized with an arbitrary sized parameter. And now we can generalize what we did a minute ago and say that from any sized generator we can get an unsized generator. Okay, and now it's easy to build a gen instance for trees just by defining the arbitrary sized operation to be gentree sized. And this arbitrary on the right-hand side, by the way, is the arbitrary for A's, which we get from the assumption that A is an instance of gen. Okay, and now at the top level we can just say quick check and state the property. And all of the filling in generators and checkers and stuff happens automatically. Okay, going a step further, as I said, we can automatically generate a lot of this stuff. So in fact, we don't need to write any of the generators for trees. We can just say derive arbitrary for tree and everything happens automatically. Similarly, we could derive show for tree, and we get a kind of generic tree display function. It may not be precisely the tree display function that makes it look exactly the way you want. So often the workflow is you use these automatic derivers when you're just setting up testing for some new project, and then as time goes on and you want, and the examples get bigger and more interesting, and the properties you're testing get more interesting, you incrementally put a bit more work into making nicer show functions, and sometimes nicer generators with, for example, distributions that you control more carefully. Adam?
Does this derived stuff work with inductive types that take functions as arguments to their constructors that return the same type?
Leo? No.
The deriving stuff works for pretty much everything except for functions. Anything that contains functions we can't really generate, we can't really print.
Yeah.
All right, so the question was, what about inductively defined types containing functions? Does that work too? And the answer is no, not very well.
You can easily generate them for some definition easily when the domain of the function is finite.
Yes, and there are tools that do that in other languages like Haskell. You can even show functions from NAT by picking a number of examples and showing its graph on that, essentially. But we don't do that here.
Okay. But we could.
We could in principle.
Yeah.
It's just we haven't found a use case for that yet.
Okay, so the end of that discussion was we don't handle functions very well in automatic derivation from inductive types, but it's mostly just because we haven't felt like putting the work into implementing it yet. Nothing fundamental. Nothing fundamental involved in doing it for some examples. Okay. Here's a slightly different topic, but very useful. So a few slides ago, we observed that the first definition that we gave for gen-tree sized generated too many leaves. And in that case, it was pretty easy to see that it was generating too many leaves. In other cases, it can be a little more subtle to see that the distribution is not tuned the way you want it. And it's useful to have the ability to collect statistics in a more rigorous way. So for that, we again follow the lead of Haskell Quick Check and introduce a combinator called collect. So collect takes a checkable property and a type A that is showable, and gives us a checker based on an instance of each of those things. So basically, it's a way of wrapping a checker in a widget that remembers the values that are being generated and allows statistics to be presented at the end. So for example, easier to see this by example, if we define a size function for trees and we write a property that says, so the fundamental property here is just true. So this property is never going to fail. But we wrap this trivial property in something that collects the size of each of the trees that it sees. And now if we run quick check on this funny tree property, we see the distribution of tree sizes very clearly. Namely, about half of the trees, we generate 10,000 examples by default, and about half of those examples are size at most 1. Right, so from that information alone, it's clear that that generator is not going to do a very good job with testing. Whereas with our better generator, we still generate quite a few trivial trees, but only around 15%. And all the rest of them are distributed pretty evenly over much larger sizes. So this generator is clearly going to do a much better job on testing. It's going to find counterexamples much more efficiently. Should we worry about the number of zeros? Maybe. But 15% of the tests getting thrown away because they're trivial, it's not necessarily that bad. We're still going to get effective testing, at least of this kind of simple properties. Okay. Next topic. The properties that we've been writing down have been pretty simple. When you try to test more complicated properties, things can get more interesting, and in particular, when you're testing properties that look like implications, where the left-hand side of the implication is seldom true, you can run into problems. So let's see an example. Here is a function for testing whether a list is sorted. It's exactly what you expect. It walks down the list and checks whether each element of the list is less than the one after it. Here's a function for inserting elements in a list. And suppose we want to test insert by checking that if the list we give it is sorted, then the list that it produces is also sorted. So this would be an important property if we were reasoning about, say, an insertion sort algorithm. We would want to know this. And indeed, if we try to quick check this, we find that it passes 10,000 tests, and along the way, we discard almost 20,000 tests. Why do we discard tests? Well, because if we apply insert spec to a list that is not sorted, then that test kind of trivially succeeds because the left-hand side of the implication succeeds. I'm not showing you the definition of this implication combinator, but it's easy. easy to define. So the fact that it succeeds in a trivial way is actually something that we care about when we're trying to think about the effectiveness of testing. So here, we're only getting useful information out of the third of the tests, and the 2/3 of the tests are just garbage. So for that reason, QuickCheck internally distinguishes between two different kinds of success, namely this kind of success that is really a kind of failure, and real success that means we tested something meaningful and the test passed. So and summarizes the results separately so that we can realize that we're not necessarily getting very good testing. Okay, so moreover, so this is already telling us that something funny is going on that we need to fix. But something even funnier is going on. Is anybody bothered by this fact that we're throwing away 2/3 of the tests? Leo is. Anybody else? Some.
Good rate, I would say.
Sorry?
It's even a good rate.
Yeah, it seems like a pretty good rate, given that the thing on the left-hand side there is testing whether the list we gave it is sorted. So what this implies is that 2/3 of the lists in the world are sorted. Well, something is really wrong. So let's find out what's wrong. Let's collect some statistics on this testing that we've just been doing. So we're still passing 10,000 tests and throwing away almost 20,000, and we also get some statistics printed. And now it's clear why this is happening, because the vast majority of the inputs are really small. So of course, a lot of them are going to be sorted. But by the same token, they're not giving us very interesting testing. Okay, so in situations like this is when we really don't want to use the automatically provided by type class magic generators. We really want to write our own custom generator. So here is a custom generator for lists that is guaranteed to return sorted lists, guaranteed by the way that we wrote it. So so if we're generating a zero-size list, again, it's sorted lists of a given size. If we're generating a zero-size list, that's always the empty list. But then, otherwise, we use some extra parameters, low and high, and generate something between low and high, if that's possible. So we choose between low and high, and then generate a sorted list between what we chose and the old high. You might still imagine that there's a problem with the distribution of these, and indeed these lists are not perfectly distributed. And there's an exercise if you choose to think about how to generate better distributed lists. But these are at least much better than what we had. Adam.
So most of the functions that you want to work with here would be naturally polymorphic, and it would seem like we should be able to take advantage of that to know, for instance, for the given length of the list, we only need the first n numbers or something like that. There's no way we distinguish between them. Do any of your generators take advantage of that?
Yeah, so the question is, a lot of properties of interest are probably polymorphic in the sense that it doesn't really matter what the actual values in the list are. It just matters how they're related. And so we probably wouldn't need very many actual values. There is definitely discussion of that kind of thing in the QuickCheck community. And Leo, what is our current status of incorporating anything like that into QuickCheck?
We have similar, enumeration testing is a very good idea, and having smaller values is a good idea. We're about to incorporate